Physics, Unit 21, Part D as in Dave. Connecting simple circuits, a single resistor with a single capacitor in series in what we call an RC circuit, resistor capacitor circuit. We've done capacitors with other capacitors, we've done resistors with other resistors, and those circuits can be simplified. Here you can't really simplify the circuit because it would be like adding apples to oranges. You cannot combine a resistor with a capacitor as far as simplifying a circuit, but they do work together to provide functions like smoothing out alternating current, storing energy, flashing lights, providing windshield wiper delays, functions in heart pacemakers to help the heart keep its rhythm when needed, helping in tuning radios. But as far as the math goes, we'll be dealing with this equation right here, where we have what's called a time constant for an RC circuit, where R is the resistor, the resistance in ohms, C is the capacitance in farads. We'll do some example problems here in a few minutes, but the time constant is kind of like, it's a little bit like dealing with like half-life for radioactive decay. The time constant is the time period for which the capacitor will discharge or charge to 63.2% of its capacity, whether you're charging or discharging. And there's a couple of fancy equations that we'll talk about, but this one right here is not the fancy equation. It's just a simple time constant. But for example, down here, kind of relating this to half-life. It's not a half-life, it's a 62.3% life. So after one time constant, basically if you're charging a capacitor, it will be charged to 62.3% of its capacity, which leaves 37.7% left to charge. So in the second time period, so let's say the time constant is 1.5 seconds. So after 1.5 seconds, it has that much percent of charge. Another time constant will be another 1.5 seconds, so a total of 3 seconds has to pass to get two time constants. You have the original 62.3% charged plus 62.3% of the remaining 37.7% that wasn't charged in the beginning. So if you add that all up, you get to 85.8%. And then you keep adding another 62% for each time constant. After three time constant periods, you get a 94.6%. After 4 time constants, it's like around 98%. And after 5 time constants, it's like 99%. The implication is that you actually never get to full charge, but you get close enough to call it fully charged or fully discharged. Same happens in reverse. So here's a chart and some graphs that show you the charging and discharging of a capacitor. This middle column shows you after one time constant, its voltage is charged to 63% of its maximum. So now the current has been reduced, so the current goes down. All right, the voltage goes up to 100% after 5 time constants, 99%. The current goes down to about, 0% after 5 time constants. They're just the reverse of each other. If you add those two columns up, they're 100%. So the current's going down at basically the inverse rate that the voltage is going up. The last entry in this table shows you how much time it takes to get the 50% charge, or to reduce the current to 1/2. 0.7 time constants. RC is the time constant. So these equations down here show you the exponential fit, and the computer will do this for you if you need to do it in the lab. The exponential fit for the time constant increase of voltage, the increase in potential difference for the charging of a capacitor, and how the current goes down by that exponential. Or discharging, there's a slight variation in the equation. For discharging, the voltage at time t goes down by this exponential curve fit, with the letter e, the irrational number e to the negative t over RC. The RC is the time constant. So to analyze that deeply, you have to use natural logs and so forth, which the computer will do for you if you have to do that in the lab. We'll be sticking with figuring out the time constant, which is R times C. Now, also along with this, let me see, I'm skipping ahead here a little bit. Whoops. All right. when an uncharged capacitor is connected to a voltage source, it acts like a short circuit, like over here. It basically has zero resistance for the first instant. But like I've said, after 5 time constants, it's like an open circuit. It stops the current from flowing. So in this circuit right here, original circuit, let's say this battery is 15 volts. Let's say this resistor is 5 ohms. When you close this switch at that very instant, 15 volts, 5 ohms, V equals IR, you'll get 3 amps of current immediately because the capacitor will be like it's not there. It's like an open circuit. So you'll get 3 amps of current flowing. That'll be the initial current. The capacitor will have 0 voltage, 0 charge, 0 anything. But as the current starts to flow, it'll start charging the capacitor. The capacitor will go from 0 volts to 15 volts. It'll match the battery. The resistor, conversely, will go from 15 volts down to 0 volts. As the current reduces, it will have less and less voltage. The potential difference will be measured, recorded at the capacitor. So after 5 time constants, you will have, as it shows here with this equation, the voltage of the resistor will be 0, the voltage of the capacitor will be 15. Those numbers have to add up to 15. At the beginning, when you first connect it, the resistor has all the voltage. It goes from 15 to 14 to 13 to 12. After 1 time constant, it'll be only like 30-some%. After 1 time constant, the capacitor will be at 63.2% of its final voltage of 15. Then once you have this charged, okay, you can discharge it, and the reverse happens. But when it discharges, the battery's not there, and the capacitor acts kind of like a battery, a temporary battery, but its voltage doesn't stay at 15. When you're charging, the battery stays at 15, and the voltages alternate from the resistor to the capacitor. They add up to 15 because they always have to add up to the battery voltage according to Kirchhoff's laws. But when you discharge it, the capacitor is 15. It goes from 15 down to, it'll lose 63% of that after 1 time constant. But the resistor will have the same voltage as the capacitor because they have to add up to 0. One's positive, one's negative. And they both reduce from 15 down to 0. And there's no voltage source at the end, so they're both 0 volts at the end of the discharging process. And once again, the equations for the actual fits to the data will be these exponentials, and a computer will do that for you if you need to do that on the lab. But in the meantime, we'll just be dealing with the basic straightforward math of the time constant, tau equals R times C. So you have a capacitor with a time constant of 0.12 microseconds charged through a 0.0350 ohm resistor. What is the size of the capacitor? Well, this is pretty straightforward. We got 0.120 times 10 to the negative 6 time to charge equals 1 time constant equals R, 0.035 ohms, just 350 ohms. That's the standard units times C. So you just divide both sides, and you end up with 3.4 times 10 to the negative 7th farads for the capacitance of that capacitor. That's part A. So that's pretty simple. Okay, I think I made a mistake there. I went back. I think that's 3.4 times 10 to the negative 6th, not negative 7th. You can double check that once you do the math there. So that'd be 3.4 microfarads. And part B, what if you now charge, that was discharging through with a total resistance of 0.0350. But what if you have to charge it with a charging resistance of 50 kilo ohms? So this is pretty typical. The time constant's greater for charging than discharging because you have some extra resistance there. So for charging here, it's a time constant of charging through an RC and a resistance of 50,000. That's 50,000 because the kilo is 1,000 times the capacitance. It's still the same capacitor. So that's not going to change. 3.4 times 10 to the negative 6. What's changed is the resistance. Instead of 0.0350 ohms, it's 50,000 ohms, a big difference. This comes out to be, I believe, 0.17 seconds. So it would take 0.17 seconds to get to 63% of its maximum capacity. After 5 of those, it's pretty much fully charged. So just under a second. It takes just under a second to become fully charged. For all practical purposes. All right, so now we have a flashing lamp. It has a RC discharge of a capacitor through a resistance. The effective duration of the flash is 0.150 seconds, during which it produces an average of 0.685 watts with an average of 2.50 volts. So this is a review question plus application of RC circuits and time constant. What energy? Well, it's 0.685 watts. It's joules per second for 0.150 seconds. So, well, we're going to be using power equals energy over time. Or in other words, energy, that's E. Energy is power times time. E equals PT. All right, we've been using that a few times in this unit. So the energy that's released is 0.685 joules per second, that's watts, that's standard, times 0.150 seconds. So I didn't write down the units, but I will in the answer. So that is 0.10 joules. 0.10 joules of energy released or dissipated. Part B, how much charge moves through the lamp? So B, it seems like I want to use I equals Q over T. I'm looking for Q. I know the time. I don't know I. However, I do know from electrical power P equals VI. And I'm given the power of 0.685. 685. Not 865. 0.685 equals, and there's an average voltage of 2.5 volts, all good standard units, times I. So I can figure out the current. The current comes out to be 0.27 amps. All right. So I can go back over here to the left and plug in 0.27 equals Q over the time, which was the 0.15 seconds for the duration of the flash. So Q, is 0.041 coulombs of charge passes through during that time. All right, part C, find the capacitance. Well, C equals Q over delta V, or V. So the charge stored here is 0.041 coulombs, we just got that, over the 2.50 volts. So the capacitance is 0.016 farads. And then part D, what is the resistance? Now we can use the time constant, tau equals RC. Basically, it's an effective time length of what, 0.25 seconds? Actually, no, what time? Oh, 1.15 seconds. 0.15 seconds. Okay, so tau equals, oops, I have the 0.15 seconds. 0.15 seconds equals R times 0.016 farads. So R magically appears as 9.4 ohms of resistance. So there we have RC circuits, time constant, charge and discharge time, and the percentages of charge that, or capacity for each given time constant, and some practical applications of RC circuits. And up next, Unit 22, magnetism, electromagnetism, magnets, a lot of fun. See you in Unit 22.